Hello everyone, welcome to Chemazon Complete Chemistry. So in our today's video, we are going to solve some of the previous year questions of GATE chemistry exam. That is some questions asked in this year's GATE 2020 exam and some questions from 2019, that is last year's paper. So this is the first question that I picked from a GATE 2019 or 2019 paper. Among the following compounds, the number of compounds that do not exhibit optical activity at room temperature is. So here you can see there are 6 different types of molecules that are given to you, and you have to identify how many of them are optically inactive or they are achiral. So first one is a very simple tetrahedral carbon. The second one is an alene molecule that we had already seen. This is a cyclic system, that is a cyclohexanone with a methyl group attached to it. This is normal wedge dash formula. This is the biphenyl system we had already seen, and these are a new class of compounds that we will be studying in our further video. These are called as cyclophanes. So let us see the first molecule. This is very simple. This is a carbon which is attached to 4 different groups, that is the phenyl, methyl, methoxy group and the hydrogen. That's why it is called an asymmetric center, and this is a chiral molecule, so it will be optically active. So this is not our answer, because in question it is asked how many molecules are optically inactive or achiral. Let us see the second molecule. This is an alene system. Here you can see there are 3 double bonds, that is odd number of double bonds, and we had already seen in our previous video of cumulines that the alene molecules or cumulene molecules containing 3 double bonds or odd number of double bonds will have a plane of symmetry passing through the entire molecule, or a molecular plane passing through this molecule, and make the entire molecule achiral. So there is a plane of symmetry present, so it's optically inactive. Let us see the next molecule. Here you can see this is a chiral center which is attached to 4 different groups: methyl, hydrogen, this carbon which is attached to a carbonyl group, that is C double bond O, and here this carbon is attached to 2 hydrogens and 1 carbon. So this is a chiral center, so it is optically active, so this is not our answer. Let us see the next molecule. So this is a biphenyl molecule, and we had already seen that in a biphenyl system there are 4 ortho positions, that is this 1, 2, 3 and 4. So all the 4 ortho positions, or at least 3 of the ortho positions, should be substituted by larger groups. So that was the criteria for optical activity in biphenyls, but here you can see that there are 3 smaller groups, that is fluorine, hydrogen and fluorine. 2 fluorines and 1 hydrogen are smaller groups, and that's why these 2 phenyl rings are very possible to remain in one single plane, and a molecular plane can pass through this molecule. Otherwise, when bulky groups are present, both these phenyls are in perpendicular planes. So this biphenyl is optically inactive. Next, this is a molecule. So this is a molecule given in the question. You can just by looking at this molecule, you might say that it is chiral molecule, but as you can see there are 2 chiral centers. But when you convert it into Fischer, this we will be learning in our further videos how to do interconversions of different projection formulas. So this is how this molecule would look in Fischer projection formula. The name of this molecule is mesotartaric acid, and in this molecule you can see there is a plane of symmetry passing through this molecule and cutting this molecule into 2 equal halves. So such type of compounds in which a plane is passing in between the 2 chiral centers, or cutting the molecule into equal halves, such a plane is called a mesoplane, and such compounds are called inactive, will be optically inactive because of presence of this plane. And this molecule will be optically inactive also because of something called as internal compensation, that is the optical activity of this carbon will be compensated by this carbon internally. Internally means within the same molecule there will be some optical activity for this carbon and there will be some optical activity for this carbon, but they will internally compensate each other, and that's why it is called as internal compensation, and this molecule will be optically inactive. Although by looking at it, it would look optically active, but it is optically inactive. So these are cyclophane types of compounds. So this is how this molecule would look in a 3D structure or a ball and stick model. The upper portion that you can see, that this benzene is attached to 2 carbons, and again to this phenyl ring attached to 2 bromo groups. So this would look something like this. The above portion, that is this carbon and this benzene ring, will be in one plane, and then this ring and these 2 carbons are in another plane. So how this molecule would look like if you see from this side. From this side, if you look the molecule, it would look something like this. And in this view, it's very clear that a plane will be passing through this molecule and making this optically inactive. So this is optically inactive. So let us summarize. Out of the 6 molecules, the allene system with odd number of double bonds, the biphenyl system with 3 smaller groups, and this mesotartaric acid. So all these 4 molecules, okay, this is optically active, and there were 2 more molecules, another which was an cyclophane compound which was optically inactive. So out of the total of 6 molecules, there are a total of 4 optically inactive molecules. So the answer is 4. So this is the question I've picked up from GATE 2020 paper. Absolute stereochemistry of the given compound is. So this is the molecule which is given to you, and they have marked 2 chiral centers, that is 4A and 8A. So at these 2 chiral carbons, you have to find out the absolute configuration or R and S nomenclature. So let us see the first carbon, that is 4A. You can see that this optically active or chiral carbon is attached to 4 different groups, hydroxyl, and 3 carbons are the primary atoms. When further you compare the secondary atoms, this carbon is attached to this carbonyl oxygen, that is C double bond O, carbon and carbon. So 3 carbons. So this will get the second priority. Hydroxyl gets the first priority as oxygen is higher in atomic number. This will get the second priority. Now comparing this carbon and this carbon, you can see that this carbon is attached to 2 hydrogens and 1 carbon. This carbon is again attached to 2 hydrogens and 1 carbon. So we move on to the next carbon, that is this one. This carbon is again attached to 2 hydrogens and 1 carbon, whereas if you look here, it's a carbon-carbon double bond. So this carbon is attached to 2 carbon and 1 hydrogen. So this will get the third priority, and this will get the fourth priority. So on moving from 1 to 2 to 3, it is clockwise, but you can see that the fourth priority group is in the plane. So we do even changes. This rule we had already seen in our very first video of RS nomenclature rules. So what I have done is we replace these 2 groups, 2 and 3, and also we switch one more, that is 1 and 4. So accordingly, this is the final structure, and now in this molecule we have done this exercise to bring the 4th position group on the dash bond. So from 1 to 2 to 3 it is anti-clockwise, so it is 4AS. So the absolute configuration is S. Now let us see at 8A. So here you can see again this carbon is attached to 4 different groups, that is the aldehydic group C double bond OH. Here there is this ketone C double bond O. Here there is CH2, and here there is this CHOH. So now let us see this carbon. Okay, so the primary atoms are same, that is carbon. So now we have to see those carbons are attached to which atoms. So this carbon is attached to 2 oxygens and 1 carbon. This carbon is again attached to 2 oxygens and 1 hydrogen. So this will get the first priority, this will get the second priority. Now comparing between this and this carbon is attached to 2 hydrogens and 1 carbon, whereas this carbon is attached to 2 carbons and 1 oxygen. So here there is 2 carbon, 1 oxygen, here there is 2 hydrogen, 1 carbon. So this will get the third priority as oxygen has higher atomic number. So from 1 to 2 to 3 it is anti-clockwise, but again you can see that the fourth priority group is on the plane of the paper. So again we do even changes and accordingly we get this structure. So from 1 to 2 to 3 it is clockwise and the fourth priority group is on the dash bond. So from 1 to 2 to 3 it is clockwise, so it is R. So 8AR. So our answer is 4AS and 8AR. That is the correct option is option D. Now this is another question that I picked up from GATE 2020 paper. Here you can see there are total of 6 set of molecules that are given to you and you have to identify the total number of sets of diastereomeric pairs are. So this is a numerical answer type question where you don't get options. You have to work out for each and every molecule and find out whether it is diastereomers or enantiomers or identical. Okay, so let us see the first molecule. So at the first glance, by looking at this set of molecule, you might feel that these are the mirror images, and when you would try to superimpose this molecule on this one, you will find that it is non-superimposable. So you might think that this is non-superimposable mirror images, that is nothing but enantiomers. Or if you think another way round, let's say if you consider this molecule and you rotate 180 degree out of plane, that is in 3D space, you rotate this molecule by plus 180 degree, then you would find that you will get this same molecule, right? So you might think it is an enantiomer or identical. So let us see. This is the first molecule of the first set. So let's start from here. This is a chiral carbon which is attached to 4 different groups, that is OH, H, PH and this carbon. Hydroxyl gets the first group, phenyl gets the second group, this carbon gets the third group as this is attached to 2 carbon and 1 hydrogen, whereas this carbon is attached to 3 carbons in a phenyl ring, or you can say 3 different carbon atoms, that is the phantom groups. So priority is from 1 to 2 to 3, that is clockwise, but the fourth priority group you can see is on the dash bond. So from 1 to 2 to 3 it is clockwise, so the absolute configuration is R. Now let us see at this carbon. Again this carbon is attached to 4 different groups, that is the nitrogen, carbon, carbon and hydrogen. So nitrogen gets the first priority as it is higher at atomic number than carbon. Comparing between this and this, again the phenyl will get the higher priority as it is attached to, as this carbon will be attached to 3 different carbons and this carbon is attached to 2 hydrogens and 1 carbon. So this will get the first, this will get the second priority, this will get the third priority and hydrogen gets the fourth priority. So from moving from 1 to 2 to 3 it is anti-clockwise and the fourth priority group is on the dash bond. So the absolute configuration is S. So now you might think that this nitrogen can be optically active because it is again attached to 4 different groups, that is this sulfur, carbon, hydrogen and this lone pair. No. Why? Because this nitrogen atom, we will see by a concept of amine inversion or nitrogen inversion, this becomes optically inactive. We will be studying what do we mean by amine inversion or optically or nitrogen inversion in the further video. So nitrogen is optically inactive as it undergoes something called as amine inversion or umbrella inversion and it becomes inactive. Let us see this sulfur. So till now we had seen that most of the chiral centers were nothing but carbon atoms, but many a times the heteroatoms like sulfur and oxygen can also be chiral. Now let us see how this would be chiral. So this sulfur, you can consider it as a tetrahedral structure attached to 4 different groups, that is this double bond O, phenyl, nitrogen and a lone pair. So this is very important. We are considering a lone pair as a substituent attached to this sulfur. So again we do the normal CIP rules. Oxygen gets the first priority, nitrogen gets the second priority, phenyl gets the third, and this lone pair gets the least priority on the basis of CIP rules. So from 1 to 2 to 3 it is clockwise, so the absolute configuration is R. So now let us see the second molecule of the first set. Again we start from here. We use the same rules, so from 1 to 2 to 3 it is counterclockwise, but you can see that the fourth priority group is on the wedge bond, so the absolute configuration is R and not S. Let us see the second. Here again you can see from 1 to 2 to 3 it is clockwise, but the fourth priority group is on the wedge bond, so the absolute configuration is S and not R. So again you can see at this sulfur we do the same CIP rules. So from 1 to 2 to 3 it is counterclockwise or anticlockwise, so the absolute configuration is S. So you can see that the configuration at this carbon is not changed, it is R. At this carbon also it is not changed, that is S. But you can see that the configuration of this sulfur, okay, at this sulfur it is changed from R to S. So 2 chiral centers, the absolute configuration is same, and this third center, that is the sulfur, it is changed. So such type of molecules we know are called as diastereomers. So if you miss the sulfur atom, then your answer might go wrong. You might say that it is an identical molecule. So this is a beautiful question where you have to look out for all the chiral centers first of all, not only carbons but also heteroatoms like sulfur and nitrogen. Here nitrogen is optically inactive because of amine inversion or nitrogen inversion. So let us see. So these are a pair of diastereomers. Let us see the second set of molecules. Here you can see there are 3 chiral centers. We use the same CIP rules, that is this carbon is attached to 4 different groups, that is this methyl, hydrogen, this carbon and this carbon. So let us compare between these 3 primary carbon atoms. This carbon is attached to 2 oxygen and 1 carbon. This is attached to 2 hydrogen and 1 carbon. This methyl is having carbon with 3 hydrogens. So this will get the first priority as oxygen has higher atomic number, and then this one. So 1 to 2 to 3 it is clockwise, but you can see that the fourth priority group is on the wedge. So the configuration changes from R to S. Let us see now at this carbon. This carbon is again attached to 4 different groups, that is carbon, carbon, carbon and hydrogen. So the 3 primary atoms are same, that is carbon. Now let us look at this carbon which is attached to 2 carbons and 1 carbon, so 3 carbons. This carbon is again attached to carbon, hydrogen and carbon, so 2 carbons and 1 hydrogen. Here it is attached to 2 hydrogens and 1 carbon, and the fourth priority will be to hydrogen. So this will get the first priority, this will get the second priority, this will get the third priority. So from 1 to 2 to 3 it is anti-clockwise, but you can see that the fourth priority group is on the wedge, so the configuration changes from S to R. Let us look at this third and the last chiral carbon. You can see that this carbon is attached to carbon, hydrogen, carbon and carbon. Again we compare the 3 carbon atoms. This carbon is attached to 2 oxygens and carbon. This carbon is attached to 3 hydrogens, and this carbon is again attached to 2 carbons and 1 hydrogen. So this will get the first priority, this will get the second priority, this will get the third, and the hydrogen gets the least priority. So from 1 to 2 to 3 it is counterclockwise, and the fourth priority group is on the dash bond. So the absolute configuration is S. So let us see the second molecule of the second set. Here again let's start from this one. we use the same CIP rule, so from 1 to 2 to 3 it is counterclockwise, but the fourth priority group is on the wedge bond, so the configuration changes from S to R. Let us look at this carbon now. This carbon is again attached to 4 different groups. We make use of same CIP rules, so from 1 to 2 to 3 it is clockwise, and you can see that the fourth priority group is on the dash bond, so it will be R. And now let us see at this third chiral carbon. You can see this is again attached to 4 different groups, and we use CIP rules, so from 1 to 2 to 3 it is clockwise, and the fourth priority group is on the dash bond, so it is R. So now let us compare the two molecules. So the absolute configuration, the first molecule was S, S and R. In the second molecule you can see that this S has changed to R, this S has also changed to R, but the third chiral center, that is R, is remained R. So at two chiral centers it is changed, but at the third chiral carbon the absolute configuration remains same. So such molecules are a pair of diastereomers. So now let us see our third set of molecule, that is this molecule. So again, by looking at the first glance of this set of molecule, you might feel that these are mirror images and non-superimposable mirror images. So it can be enantiomers. So are they enantiomers? Let us see. So this is the first molecule. Here again you can find out the chiral centers. There are two chiral centers. First of all, looking at this chiral center, it is attached to 4 different groups, that is carbon, carbon, hydrogen and phosphorus. Phosphorus gets the first priority as it is higher in atomic number than carbon and hydrogen. This methyl and this carbon is attached to 2 hydrogens and 1 carbon, whereas this carbon is attached to 3 hydrogens. So this one gets a second priority as carbon has higher atomic number than hydrogen, and then hydrogen gets the fourth priority. So from 1 to 2 to 3 it is clockwise, and the fourth priority group is on the dash, so the absolute configuration is R. Now let us look at this chiral carbon. So it is again attached to 4 different groups, that is carbon, carbon, carbon and hydrogen. Now let us compare. This carbon is attached to 2 hydrogens and 1 carbon. This carbon again attached to 3 hydrogens. This carbon is attached to 3 carbons. So from 1 to 2 to 3 it is counterclockwise, and the fourth priority group is on the dash bond. So the absolute configuration is S. So now let us see the second molecule. Again we start from this carbon, which is closer to phosphorus. This carbon is again attached to 4 different groups. We use the same CIP rules, and from 1 to 2 to 3 you can see it is counterclockwise, but the fourth priority group is on the wedge bond, so the absolute configuration is R. Let us see the second chiral carbon. We use the same CIP rules. From 1 to 2 to 3 it is clockwise, but again the fourth priority group is on the dash bond, on the wedge bond, sorry. So the absolute configuration is S. So now let us compare these two molecules. So the chiral center closer to phosphorus has R, then this has S. In the second molecule again you can see that this chiral center, which is closer to the phosphorus, has R configuration and S configuration. So the absolute configuration at both the chiral centers is the same. So these are identical pair of molecules. So let us see the next set of molecules. This is the fourth set of the question. So here you can see there are 2 chiral carbons. Let us look at this carbon, which is attached to 4 different groups, that is nitrogen, carbon, hydrogen and carbon. So nitrogen gets the first priority as it has higher atomic number than carbon and hydrogen. Methyl gets the third priority as it is attached to 3 hydrogens. The carbon is attached to 3 hydrogens. Here the carbon is attached to oxygen, hydrogen and carbon. So this will get the second priority as oxygen has higher atomic number. So from 1 to 2 to 3 it is clockwise, and the fourth priority group is on the dash bond. So the absolute configuration is R. Now let us look at this chiral carbon. You can see that it is attached to carbon, carbon, oxygen and hydrogen. Oxygen gets the higher priority, or this hydroxyl group gets the first priority as oxygen is higher in atomic number. comparing between this carbon and this carbon, you can see that this carbon is attached to 2 oxygens, in fact 3 oxygens. This carbon is attached to 3 oxygens, whereas this carbon you can see is attached to nitrogen, hydrogen and carbon. So this will get the second priority, as oxygen has higher atomic number than nitrogen. So from 1 to 2 to 3 it is counterclockwise, and the fourth priority group is on the dash bond. So the absolute configuration is S. Now let us look at the second molecule of the fourth set. Let us see this carbon. We use the same CIP rules, 1 to 2 to 3 it is clockwise, and the fourth priority group is on the dash bond. So the absolute configuration is R. Let us look at this chiral carbon. It is again attached to 4 different groups. We make use of same CIP rules. So from 1 to 2 to 3 it is clockwise, and the fourth priority group is on the dash bond. So the absolute configuration is R. So now let us compare these two molecules. You can see that the absolute configuration for this is R and S. In the second molecule you can see that this R configuration is the same, but you can see that this S configuration has changed to R. So this is again a pair of diastereomers. So now let us look at this fifth molecule. So this is the first molecule of the fifth set. Let us start from this chiral carbon. It is attached to 4 different groups, that is this methyl, hydrogen, and you can see that these 2 oxygens are same. So let us see what these 2 oxygens are attached to. So this oxygen is attached to a carbon which is attached to phenyl and hydrogen and a carbon. This oxygen is again attached to a carbon which is attached to hydrogen, deuterium and carbon. This is deuterium is nothing but an isotope of carbon. So now we have to compare these 2 groups and these 2 groups. So you know that this carbon is attached to carbon, carbon and hydrogen, whereas this carbon is attached to hydrogen, deuterium and carbon. Since this carbon is attached to 2 carbons and 1 hydrogen, this oxygen will get the first priority and this will get the second priority. Comparing between this and this is a carbon with 3 hydrogens, so this will get the third priority and hydrogen gets the least priority. So on moving from 1 to 2 to 3, that is counterclockwise, but the fourth priority group is on the wedge bond. So the absolute configuration changes from S to R. Let us see at this carbon now. This is attached to oxygen, carbon, carbon and hydrogen. Obviously this carbon is attached to 3 carbons and this carbon is attached to oxygen, deuterium and hydrogen. And the primary atom here was oxygen. So this group will get the first priority. Comparing between this carbon and this carbon, this will get the third priority and this will get the second priority, because this carbon is attached to oxygen atom which is higher in atomic number than carbon. So 1, 2, 3 and 4. 1, 2, 2 to 3 clockwise, and the fourth priority group is on the dash bond. So the absolute configuration is R. Now let us look at this carbon. This carbon is again attached to 4 different groups, that is oxygen, hydrogen, deuterium and carbon. Oxygen gets the first priority as it has higher atomic number than carbon, that gets the second priority. Comparing between hydrogen and deuterium, now the atomic number is same. So whenever the atomic number is same, we compare the atomic mass number. So deuterium is 2H1, that is it has got higher atomic mass number than hydrogen. So this will get the third priority, hydrogen will get the fourth priority. So from moving from 1 to 2 to 3, it is counterclockwise, but the fourth priority group is on the wedge bond. So the configuration changes from S to R. Let us look at the second molecule of the same set. Starting from here again, we use the same CIP rules. So from 1 to 2 to 3, it is clockwise. But the fourth priority group is on the wedge, so the configuration changes from R to S. Let us look at this carbon. Again we use the same CIP rules. So from 1 to 2 to 3 it is clockwise and the fourth priority group is on the wedge bond. So the configuration changes from R to S. Let us look at this third and the last chiral carbon. We use the same CIP rules again. So from 1 to 2 to 3 it is counterclockwise and the fourth priority group is on the dash bond. So it is anti-clockwise or S configuration. Now comparing the two molecules, you can see that in the first molecule all the three absolute configuration are R. But in the second molecule you can see that the absolute configuration is changed for all the three chiral carbons, that is, it changes from R to S. So in this set of molecule, the absolute configuration at all the three centers is changed from R to S. Hence this is a set of enantiomers. Now let us look at the last set of molecule, that is the sixth set of molecule in this question. It is very clearly visible from the examples itself that this hydroxyl, which was on the wedge, they are changed to dash, so the absolute configuration will change at this carbon. Let us look at the second chiral carbon. Here phenyl, which was on the wedge bond, is changed to dash, so the absolute configuration will again change at this carbon. But in the third carbon you can see here that the absolute configuration will not change because it is the same, that is, it is on the dash bond. So this is again a pair of diastereomers. So now let us summarize. The first molecule, we saw that there was a sulfur group which had optical activity, because of which we were misconcluding it to be identical, but it was found to be diastereomers. So the first set of molecule was very important, without which your answer would have been 3 and not 4. The second set was again diastereomers, third set was identical, fourth set was diastereomers, fifth was enantiomers, and the last one we saw just now, it is diastereomers. So 1, 2, 3 and 4. So your correct answer is 4. Thank you so much.